Hello and welcome back to Calculus 1 Saturday edition, right? We have next section on applying the derivatives, and this one is optimization. It's all word problems applied. Now, even though it's word problems, 100%, this section is very structured. The way we are going to solve every problem is the same. Now, every problem will look different, but the way you solve it is the same. We are familiar with what the word optimization means. You are trying to come up with the minimum or a maximum value to optimize maximum profit, minimum cost, minimum energy, or maximum energy, or right. So clearly, in order for us to go through these things, we are going to use first derivative equal to 0, because that's the way to find min and max, right? So where is the tough part? For most students, the tough part in this section is to translate the word problem into mathematical equation. That's the part that you have to practice. Once you have the model, taking the derivative and shoveling things around in algebra and right doing the technically 4.1 should not be issue for you. So let's take a look at the procedure, and then we're going to do some more involved problems. So the first order of business is to just take a look at the procedure, and we're going to take a look at, let's say, sum of two numbers is 100, right? So sum of two positive numbers is 100. Find x and y such that their product is maximum. This problem has nothing to do with reality. It's clearly just mathematical, manipulation to see, to just get our feet wet, what we would say, right? No one cares about such two numbers for anything. But it's a good exercise. What you see here are two sentences. Each sentence produces an equation, and you just need to solve that. It's very simple. First equation says that sum of two numbers is 100. What should I write if I know that those two numbers are x and y? What should I write? Thank you. X plus y equals 100. So you are going to have this every single time. It will say that the perimeter of the fence is, and you say, okay, I know the formula for perimeter. Now, what are we fencing off? Well, rectangular plot or a triangular plot or, right, or a circular plot, I don't care, right? We know the formulas that would be involved. So you literally translate English into math by doing this. Now, second sentence, find x and y such that their product is maximum. How would you write that? Product of x and y. What do you write? X times y is max. There we go. We just set up our problem. This equation is called constraint. And this equation is called the objective. The one that has min and max in it. Done. Now, The procedure to solve the problem. Number one, solve constraint equation for one of the variables plug constraint equation into objective equation to eliminate one of the variables. Three, differentiate resulting equation for win. That's it. That's your procedure. Now, without me solving any of the problems for you, are you able to follow the red and solve these two equations? Clearly, step number one says solve the top equation for any of the two variables. So what do you write? What do you write? Y equals 100 minus x. Cool. All right, step number one done. Step number two says plug the constraint equation into objective equation to eliminate one of the variables. That just says plug in. Well, great. That's x times 100 minus x equals the max. That's 100x minus x squared equals the max. Great. Step number two done. Right? This new equation has no y's. Every single problem is like this. If you are able to do this, looking at the text, I mean, the rest is really a facepalm if you don't do it. Because it's always going to be the same. Solve for one of the variables in a constraint equation. Plug that into objective equation to kill one of the variables. And now you have this. Now step number three says differentiate. Great. d dx. Yeah, you know how to differentiate this. What's the derivative of 100x? 100. What's the derivative of x squared? 2x. What's the derivative of a maximum? What's the derivative of maximum? What is maximum? 0, thank you. Maximum is a constant. Because let's say that two numbers that you pick are 30 and 70, right? So 30 times 70 is 2100. So max is 2100. Let's pick 100 and a 0. 100 times 0 is 0. Again, a constant. No matter what you pick for x and y, when you multiply, you always get a number. Derivative of a number is 0. So every time when you differentiate min or differentiate the max, you get to 0. Second confirmation that that's 100% same is, wasn't it min and max take the derivative, set it equal to 0? Right? Well, now we don't have to set it equal to 0. We get it for free, right? The derivative of that puppy is 0. So good, we don't have to set that equal to 0. We just have it there and just solve it. So what's x? Very good. X is 50. Now what's y? Well, you have equation for y. Y is 100 minus x. So y is also 50. And it turns out that x equals y equals 50. So what is the number which will give you sum to be 100 and product to be maximum? It's 50 and 50. You pick any combination other than that is going to be less. And you can test this. You can test this by picking 60 and 40. Thank you. You can check that in a chart. If you have a 50 times 50, which add to 100, you get 2,500. If you have 40 times 60, you have 2,400. If you have 10 times 90, you get 900. No matter what else you pick, calculus is telling you that the maximum is when x is 50 and y is 50. Now, go on, waste your life, try to prove it wrong, meaning trying every other combination of numbers that add to 100, and there is infinitely many, right? Because you can pick 37.896 times 62.104. It's still going to be less than 2,500. So it doesn't matter what you pick, okay? It's going to be less. And that's the procedure. So this is done. That's 4.4. The red procedure. You come up with equations from the text, and that should be the hard part. The rest, solve one equation for a variable, plug in the other equation to eliminate the variable, differentiate, and then I said win at the end, which is you have your values. Now clearly this is highly applied everywhere. So let's take a look at application problems. The problem that I gave to my Calculus 3 class could be done with Calc 1 as well, or the Calc 3, where Calc 1 solution is much, much easier, and I still didn't go well. So we'll take a look at that problem as well. It was the exam question. So eventually we'll get there. Let's take a look. Oh, actually, no, that problem is... Now, let's do the farmer first. Farmer problems. These are very standard, you know, like it's 90% chance that farmer problem is going to end up on one of the exams. One of the variation. We're going to do like 5 different variations on a farmer problem right now. So what is the problem? Farmer has 2,000 yards of fence. So he has this, all right? He wants to use all of it to fence off rectangular So he wants to fence off rectangular plot. Which dimensions will yield the largest area? So which dimensions are going to yield the largest area? With every applied problem, especially if you're doing physics, you should draw a diagram to make sure that you are working with the right concepts. So we have a rectangular plot. Rectangular plot with dimensions x and a y. Farmer has 2,000 yards of fence. Where does the fence go? Around. There's a reason why it's called a perimeter fence, right? It goes on a perimeter. Isn't that a one equation already? Right? It's a one equation. It says 2x's plus 2y's is all 2,000 yards of fence that I have. So 2x plus 2y equals 2,000. That's the first sentence. That's the first sentence over there. And now we go in a third sentence. What dimensions? AK, find x and y, so that we have the largest area. How's this different? The answer is it's not. All right, it's the same problem, except over here you get another 0. Once I cancel this by 2, it's the previous problem with an extra 0 at the end. So there you go. So what am I solving? My constraint equation is x plus y equals 1,000. My objective equation is xy equals a max, and this is the same problem. Solve for y, so 1,000 minus x, plug in, and you get x times 1,000 minus x equals a max, 1,000x minus x squared equals a max. Factor out x. Oh no, sorry. Hit it with the derivative first. So once you simplify everything, hit it with the derivative, and then when max becomes a 0, then you solve the equation. It's a 1,000 minus 2x equals 0. 2x equals 1,000. X equals 500. And then y equals 500. So now we learned that actually square is a rectangle with the maximum area. We learned that. Now we can obviously do that. So largest area at 500 by 500 yard. It's a word problem, so the sentence at the end. You don't have to write a 5-page essay, just a one sentence answering the question. Largest area at 500. You can also compute that area, right? If you want to. Let's make stuff more interesting. This rectangular plot is now going to be adjacent to a river, which means that one side doesn't have to be fenced. All right? So here's the river. If I put some salmon in it, then it makes, right? Salmon is red, so there you go. If the salmon goes to the left, which way is the river going? Gotcha. Depends on the time of the year, exactly. If they're going or coming back. I know, right? Eventually you're going to go home. I do it every semester. I'm a terrible person, I know. Look at this thing. We still have 2,000 feet of fence, yard. 2,000 yards of fence. Still looking for max area. Now, how's this problem different? Yeah, only 1x. So my perimeter now is not 2x 2y, it's 1x plus 2y. And that's what's different. So just be careful. I have 1x plus 2y equal 2,000. X equals 2,000 minus 2y. It doesn't matter which number you solve for first. If I go and solve for y, in this case, I'll end up with fractions. So I'm not going to do that, okay? The area is still xy equal a max. That's still the same, because not having one side has nothing to do with area, right? Area is here. And it's just, instead of a black line bordering in the top, I have a blue line bordering in the top. That doesn't matter, right, for the area. Area still remains area x times y, even though there is no top line over there to worry about. Plug in. Very systematic, guys. You look at the picture, come up with equations, plug one into another, and be done. So instead of x, now I have 2000 minus 2y. Everything times y is a max. That's 2000y minus 2y squared is a max. And this is where you hit it with the derivative, because you only have one variable. Now we are differentiating in respect to y. So that's going to be 2000 minus 4y equal 0. Remember that max is a max area. Area is a number, therefore derivative of max is 0. 4y is 2000. Y is equal to 500. Nice, right? But then we have x equals 2000 minus 2 times 500 is 1000 now, you see? So it's no longer a square. So max area at 1000 by 500 yard in this case. So square is not always an answer. So first problem was somewhere in the middle of the countryside, away from rivers and everything else. There is a rectangular plot with fence on all 4 sides. Then the farmer moved next to the river and doesn't have to use those sides. Now I'm going to have a farmer create bins. So this is the situation. Cabbage, rabbits, and tigers, let's say. All right? Can't put those in the same bin. You have to have a fence separating them, right? Or you can't put rabbits in cabbage, right? I eat the cabbage. Can you put tigers and rabbits together? No. Right? Well, if you need the rabbits, right? Because they lay eggs for the last week, right? So, anyway. So you gotta, you have to keep all of this stuff separated. So now, I still have 2,000 yards of fence. I still want the max area. Is anything changed? Vulture is back. Every Saturday. Exactly at 12. What's new now? Four y's. You still have 2 x's and you have 4 y's. It's just slight modifications. Calculations are recycled over and over and over again. So 2x plus 4y equals 2000. You will be able to divide this by 2. And you're still looking for xy to be a max. All right, solve this one on your own completely. Next one I'm just going to set up. We're not even going to solve it. Move to a different type of a problem. All right, let's take a look real quick. X plus 2y is 1000. X is equal to 1000 minus 2y. So plug in 1000 minus 2y times y equals a max. 1000y minus 2y squared equals a max. Hit this with the derivative now, d dy. 1000 minus 4y equals to 0. Y is 250. X equals 1000 minus 2 times 250 is 500. So max area at 500 by 250 yards, and you still have those two divisions, right, in between. So that means that this line over here is 500, and this one over here is 500. Now you have to divide 500 by 3 to find the locations when you are going to put these guys. Now obviously it doesn't have to be exact. Maybe you need a little bit more room for tigers than for, you know, move a little bit left or right. Poor rabbits in the middle. They look left, food. They look to the right, I'm a food. You can have any combination in the galaxy. It's just if you're able to write down the equations. You know, you can go halfway and halfway, like this. So what do you have? You have a big X over here, you have a big X over here, a big Y and a big Y, and then Y over 2 and X over 2. So what's the perimeter plus the insides? It's 2x plus 2y, that's the going around, plus x over 2 plus y over 2 equals 2000, and still xy equal a max for maximum area. And then you go and you plow through this, you know. So all of these problems are very structured. As long as you know, can get through geometry, you should be fine. Let's take a look at the one that I had for my Calculus 3 that you can also solve by Calculus 1. A box with square base and no top. Is to have volume of, and then we pick a number. I don't know, 64 feet cubed, whatever. So a box with square base and no top is to have volume of 64 feet cubed. Find the dimensions which will minimize surface area. Now, guys, there's a whole industry built around this. It's called packaging engineering. Packaging engineers design boxes to ship stuff from everywhere in the world here because we don't produce anything anymore. Right? So you want to design a box which is sturdy and large enough to contain the object, right? It needs to travel half across the world. And we also want that box to be as small as possible because that reduces cost. Sure, if I design a box that is $1 less than your design because I'm using less material to make the box, I'm the one who wins the project. I'm the one who gets the money. And you? Nope. Now you say, but it's $1. What's the big deal? It's a huge deal. Because when you ship 100,000 units, that's 100,000 boxes. $1 per box is $100,000 savings. So if they're going to save $100,000 with my design, it's nothing for them to give me 10,000, right? Because they have to pay someone to design box anyway. So why would they take someone's design that's going to cost them 100,000 more, right? So there is a whole industry. Apparently, well, it has to be a booming industry. At Rutgers right now, they say that the students are getting hired outside of that major even before they graduate. But yeah, so our school here designed one of the tracks in engineering to feed students directly into that major at Rutgers because now there is a boom, right? So that's that part. So packaging engineering, and they do things like this, and you have quite a few problems in the shipping crates and all of these kind of different things in the homework. So you'll see this is directly just a life skill that you get to cash out on directly. So what do we have? We have a box. You all have a concept of the box. We're sitting in a box. This one has a top, but it's a box. Square base. So what am I going to draw? I'm going to draw a box. I'm going to draw a bottom, right, which has X and X. And then I'm going to put rectangular sides, but I'm going to flatten them out like this. And the height of each one of these sides is Y. Now, if you put this thing together, looking from the side, you are going to have something that looks like this. Right, that's the box. And you can see inside there is no top. What's the volume for this box? X squared times y equals 64, and there's your constraint equation. Constraint equation is the one without min and max. What's your surface area? That's where you look at this, right? What's the surface area? What's the area of 5 rectangles you have there put together? 4xy, that's the sides, plus x squared in the middle. And you want that to be minimum because the text tells you that you want to minimize this. Minimum amount of material, minimum cost to make that material, reduces the cost of the whole project. Ta-da! Right? Solve it. Clearly you're going to say y equals 64 over x squared. Stick it in here. Differentiate, be done. Let's go. Do what? Because it is, I'm sorry. It's math. I was looking for and I don't have To solve the top equation, y equals 64 over x squared. Replace the other y with that 64 over x squared, cancel, differentiate, and be done. All right, so there should be plenty of time. We take the constraint equation, y equals 64 over x squared. Then we plug that into our objective equation, so that's 4x times 64 over x squared plus x squared equals a minimum this time. X and square would cancel. 64 times 4 is, very good, 256. Divided by x plus x squared equals a minimum. As soon as you get rid of the second variable, and as soon as you simplify everything, this is where you hit it with the derivative. So derivative over here is negative 256 divided by x squared plus 2x is equal to 0. To solve this, you ship 256 over x squared to the right. Cross multiply, move the 2 to the right, so we have x cubed equals to 128. Good enough, right? That's 64 times 2, right?
Yes.
And 64 is 8 times 8 times 2. So this is, when you take the cube root, it's 4 cube root of 2. That's what it is. You can come up with a decimal if you care. I don't. So that's that. And now I have y that needs 64 over 4 times cube root of 2 squared. That's y equals to 64 over 16 times 2 to the 2/3. 64 and 16, they cancel. You cancel by 8. So that's a 4. So y equals 4 over 2 to the 2/3. So minimum area for 4 cube root of 2 by 4 over 2 to 2/3. Now if you calculated decimals, feet, right? If you calculated decimals, we can take those answers as well. This is exact. Let's take another problem and then switch a section. So last problem is 29. What you have is a flower garden that has a patio around it that you can walk. It says surrounded by a grass area. Could be bricks, could be concrete. This could be a pool with a walkway around, but it could also be a page with margins. When there is the design for your textbooks, right? More pages, more paper, more cost. Bigger the margins, less you can put on the page. If you put margins that go all the way to the end of it's not good. So all of these things are calculated, guys. This is highly cashable section, okay? Figure this out, and a lot of opportunities down the line if you figure all of this out. So I don't care what kind of problem we have. It's just a rectangle within the rectangle. What the book has is a rectangular flower garden in the middle, with the grass on the outside. So that's grass. And this is where the flowers are. You don't want me being in charge of this because that's what you get. All right. So now what do we have? They say that over here is 2 meters. Over here is 1 meter. Over here is 2 meters. Over here is 1 meter. A rectangular flower garden with area of 30 meters squared, great, that's given, 30 meters squared in here, is surrounded by this. What dimensions will minimize combined area? All right. Looking for the minimum on combined, right? Yeah. Well, I have to put some some variables so I can work with this. I'm going to call the inner one x and the inner one y, because that will immediately give me my constraint equation xy is 30. And I also want to now write what is the equation for this side if the one inside is x. What's the one on the outside? X plus 4. Because you see that you have to add 2 to each side. You have x in the middle, plus 2 on one side, plus 2 on the other side, is x plus 4 for that side. And how about the vertical one? Y plus 2, nice. So now we want the outer area to be minimum. So this is x plus 4 times y plus 2 equals a minimum, right? That's what we want. If you're able to go this far, the rest should be a joke. Either x or y is 30 over whatever the other one is. Plug in and you're done. Now, would this make sense as a flower garden? No. But does it make sense if you are creating a textbook and you're solving this? And the answer is yes. I just picked up a paper over there in the printer, and as you can see, it has a formatting on it. Right? This is what your project is going to look like. Well, more like this, but all right. So now, you don't have to have 2 columns. So now, you see the margin. Your textbook has to have the text inside. That's what the book's for the text. So the 30 meters squared is whatever the area for the text is. Clearly, you want to preserve that surface area while making the page as small as possible. Because smaller page, less paper, less materials, less cost. See that? So, as a flower garden, this problem is garbage because no one cares, right? You say, I have some land over here, I want to put some flowers. Great. No one does calculus for that. But you get hired and paid to figure out the margins and figure out the exact dimensions of the book so that you can minimize the cost of the print. Smaller book, less weight for shipping, transporting, less room for storage in a warehouse. There's a reason why online shopping is destroying everything, right? Babies R Us, Toys R Us, what's closing now? Walmart shut down a store on 22, right? Why? Amazon is destroying them. Amazon is starting their own space company. This is how, do you know how much money you need to start a space program? They're starting their own space company. This is how much money they make. It's insane. What are they paying? Do they have massive stores with lots of people working with electricity going on and everything else? Would they have to pay for the rent and tax, property tax? No. All they have is a warehouse with whoever working in it. That's it. Right? Zero qualifications technically. That's what they have. And maintain someone to just keep the website alive. Right? Think about Best Buy. The amount of people that work there and stock the shelves and make everything look pretty and design and bathrooms and everything that you have to run the store. That's why they're dying, right? So, optimization, right? That's what you're learning. So what do we have? Whatever, x equals 30 over y. It doesn't matter which one to solve for. So that's 30 over y plus 4 times y plus 2 equals a minimum. I am going to distribute this. I don't want to do product rule for no reason. So times y, that's just 30, plus 4y, plus 60 over y, plus 4y, no, plus 8, equals a min. All I have is 30 times 30 plus 8 is 38, so 4y plus 60 over y plus 38 equals a min. All right, I have one variable, simplified equation, d dy. So what do I have? 4 minus 60 over y squared. Derivative of 38 is 0. Derivative of a min is a 0. To solve this, 60 over y squared is equal to 4. Cross multiply 60 equals 4y squared. Y squared is equal to 15. Y equals positive negative root 15, but can have negative, the lengths are not negative. I got my y. Equation for x is 30 over this. So x equals 30 over root 15. Remember, we are not happy with root 15 in the denominator. So rationalize. Root 15 times root 15 is 15. Cancels with the 30. It's 2 root 15. Min area at 2 root 15 by root 15 meters. That's the answer. Every problem is the same. Look up at my... What happened? 4. Y plus 4. X is equal to...
So your main equation is x plus 4. Y plus 2. No.
Oh, you are right. This is so terribly wrong. You are right. I calculated x and a y. That's the inner. Yes, I have to add 2 and 4. Yes, yes, yes. Mean area. So, wow. So y is root 15 plus 2. So mean area at 2 root 15 plus 4 by root 15 plus 2 meters. There we go. Great. Yes. Yes, yes, yes. X is plus 4. Yes. Okay. Nice. You have a whole bunch of problems to practice. If you are able to separate them like this, That's that. 4 steps. Model, eliminate variable, derivative, solve the equation. Recycle, 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 recycle. All right, next section.